wabarakatuh. We are students from Group CS24851. The topic that we choose for vector calculus group assignment is Green's theorem to solving line integrals over plane regions. Before we begin, this is the list of our group members. I am Nur Christina binti Hashim. I will start by giving a quick introduction to Green's theorem. This theorem was introduced by George Green back in 1828 based on his study in electricity and magnetism. Even though he wasn't well known during his life, his work was later developed further by Cauchy and William Thomson. Green's theorem is useful because it changes a line integral around a closed curve into a double integral over the region inside that curve. This makes calculation much easier, especially in physics and engineering. Now, let's take a look at the theorem shown on the right side of the slide. Green's theorem applies to a simply connected region with a closed and smooth boundary, which we call C. This curve must be oriented in counterclockwise direction. The function involved pxy and qxy along with their partial derivative must be continuous throughout the region. As you can see in the diagram, the curve forms the boundary of the region, and that is the area over which the double integral is evaluated.
Hi, my name is Nurul Nabila binti Suhaimi. Now let's continue with the two questions related to our topic, which is Green's theorem. The first question is, an engineer is designing a triangular solar panel mounted flat on the ground with corners located at 0, 0, 1, 0 and 1, 1 meters. To study wind flow across the panel, the engineer wants to calculate the circulation of a given vector field fxy equals to y square I plus x square j along the edge of the triangular solar panel that travels counterclockwise. Evaluate integral of f dot dr using Green's theorem. The second question is, a weather research station is analyzing wind patterns around a circular park with a radius of 2 km centered at the origin. The wind vector field in the area is given by fxy equals to 3x plus yi plus x plus 2yj. The scientists want to compute the circulation of wind around the park's boundary to assess rotational wind behavior. Use Green's theorem to evaluate integral of f dot dr, where c is the boundary of the region bounded by the circle x square plus y square equals to 4 and oriented counterclockwise.
Assalamualaikum, my name is Raja Nurul Alia binti Raja Iskandar. Now I will explain the solution for question 1. On my left is the manual equation, and on my right is shown the output from Maple software. So first, let's evaluate the line integral using Green's theorem. But according to Green's theorem, we can convert a line integral over a closed curve C into a double integral over the region R it encloses. In our case, P is equal to y square and Q equals to x square. Then we compute the partial derivative 2x minus 2y and substitute it to the formula. Next, we need to define the region R based on the limits shown. It is the triangular region bounded by the x-axis, y-axis, and the line y equals to x from x equals to 0 to x equals to 1. So we write the double integral, then we integrate with respect to y first, which simplifies to 1 over 3. So the final answer is 1 over 2 over 3, similar to the maple output.
In this problem, we asked to evaluate a line integral using Green's theorem. We start by identifying the component P is equal to 3x plus y and Q is equal to x plus 2y. By using Green's theorem, we convert the line integral into a double integral over the circular region x square plus y square less than or equal to 4. We then calculate the partial derivative of Q is equal to 1 and partial derivative of P is equal to 1. By substituting this, the integrand becomes 1 minus 1 is equal to 0. So we are integrating 0 over the whole region. That means the result of the integral is 0. Therefore, the final answer is
In
0.
conclusion, for question 1 first, which is triangular panel, the non-zero circulation 1/3 indicates some rotational behavior or vorticity in the wind field around the triangular panel. This might imply local swirling or curved wind flow patterns that could affect the panel's efficiency or structure. Meanwhile, for question 2, which is circular part, the circulation is 0, meaning that the net rotational behavior around the part is 0. The vector field is balanced and likely conservative with no net swirl that suggesting calm or stable wind behavior along the boundary.